uniform motion. Uniform motion is when something travels an equal distance in equal intervals, or in other words, when the velocity is kept constant throughout a certain period of time. As previously seen, we used a remote control car to demonstrate this. We measured a straight line track that measured 3 meters in from start to finish and timed how long it took for the car to complete the track. As shown below, you can see it took 1.12 seconds for the car to complete the track. Now, because the car is a demonstration of uniform motion, there's only one kinematic formula that corresponds to it. The formula is V equals d over t. And because we have the distance and the time it took for the car to cross the track, we can find the constant velocity of the car. All we have to follow is our kinematic formula. Our d would equal 3.0 meters and time equals 1.12 seconds. So when we divide these, 3 divided by 1.12 seconds, we get on our calculator 2.678 meters per second. But because it's significant digits, we have to change it to 2.7 meters per second because 3.0 is the least amount of digits we have. Now, with the information we have now collected, we can make graphs to display this. Now, this position time graph shows your position or distance versus the time it took to complete the track. This graph is also a perfect example of uniform motion for a position time graph because of the line it forms. As we know, position and time graphs for uniform motion will always form a diagonal line, which as you can see below, our graph forms a perfect diagonal line. Now for a velocity time graph. It follows a different pattern of the line. As we know, velocity for uniform motion remains constant throughout the period of time. Now, as we can see on the graph shown below, that's exactly what is shown. We have our velocity gathered by our kinematic formula, V equals d over t, in which we have discovered it to be 2.7 meters per second, which is shown, showing how the race car is moving in uniform motion. Now, on to acceleration.
Acceleration. What is acceleration? Acceleration is a name we give to any process in which the velocity changes over a period of time. Now, in the video shown beforehand, you can see how acceleration caused by the gravitational pull of the Earth affects the velocity of the pumpkin as we throw it off the balcony. Now, unlike uniform motion, acceleration actually has 5 kinematic formulas in order to determine your missing variables. As shown below, you can see all 5 formulas that can determine your missing variables. In our video shown previously, we can obtain data from the free fall to determine our variables so we can solve and then fill it in for a graph. That's going to be our acceleration. Now, we also know the velocity at which the pumpkin was dropped because it was just a free fall, so it didn't have any starting point, it was just at a 0. So that we also fill in as one of our givens. Now we also have the time it took for us to drop this pumpkin. It took us approximately 0.79 of a second, so that we also put down as our given. So now that we have all this information, we're actually going to be looking to the placement of the pumpkin when it hit the ground and how fast it was going. So we're looking for V2. Now, in order to figure out which kind of kinematic formula we use for the information we provided, we then have to look at our kinematic formula, which you can see again here. So what we're going to do is we're going to figure out which one formula does not have distance. We don't have distance here, so we don't need it. Therefore, we have to look for the equation that doesn't have it. So in this case, our equation would actually be Now that we have our formula and our information, all we have to do is fill it in. Now, all I've done here is I filled out my variables into my formula so I know what's going on. My v1 I knew equals nothing, so we fill that in. And my acceleration was negative 9.81 because that's the acceleration of gravity. And then we have our time, which we found out, which was 0.79 seconds. As seen below, you can tell that that was our time when we timed a pumpkin bomb. Now, once you fill it in and do the math, all you do is you times your acceleration by the time you found out. And we discovered that it was actually negative 7.7499 meters per second. However, we can't leave that number because of significant digits. We look and see there's 3 significant digits in this one, and there's 3 significant digits in the time. So we know we use the shortest amount of significant digits in our formulas, in our givens. Where this, both of them being 3, we know we have to have 3 significant digits in our answer. So we would just use our V2 would equal negative 7.75 meters per second. Now, you could say negative or you could say down because that's what it's going. So you can leave it like this, but the proper way to put it is .75 meters per second. However, now what we're going to do is we're going to fill this into a graph. But we need more than just the 1 point. This is just our final position on our point. But we need more than that. So what we're going to do is we're going to do the exact same formula over. The only difference is we're going to use different points for the time. So the way I would do it is I would take this 0.79 and say, okay, now I need to find different points for up until 0.79. So what's the best way I can do that? I can put my points in for 0.01, which means I would just use the exact formula over. The only thing different is I would change my time for 0.1. And I would do the formula out over and over again until I got this. Then what I do is I'd fill in the points for the graph, which is exactly what I've done. If you look down here, you can see my information and my formulas for how I would get each point that I later on put in the graph. You can see how I followed the formula down, and I just used different points on my graph. Now, if you look back, this is where the graph would be. All I did was I took every single point that I used that I got into my information beforehand, and I filled it in for a graph. This is used so you can see the change in position during your acceleration. Now you can tell it's not exactly diagonal because you do have little bumps. It's not directly straight because you're not having a solid position moving at a solid velocity. Your velocity is always changing with acceleration, which as you can see below. Now we'll be discussing velocity time graphs with acceleration. Now, as we can see here, all I've done is I've taken my givens here and I filled them in for my variables, which I got from my formula. So we have 2, and then we have our acceleration, negative 9.81 meters per second squared, times by our distance of negative 6.0 meters, which that equals v2 to the square root of 2 minus 0, because our v1 is actually 0. Now, 2 times negative 9.81 meters per second squared gives us 19.2 meters per second squared, times our negative 6.0 meters, which equals v2 to the exponent of 2. So all we have to do is we times it. Now this will equal, once times, 19.62 times negative 6.0 meters This will give you about 117.72 meters per second. Now all we do is, because we have our v2 and it does have an exponent of 2, in order to get rid of that, we just have to square root both numbers, which, as you can see, that down here. So once this number, 117.72 meters per second squared, is squared, it gives you approximately 10.8 meters per second. Now you just use your calculator to figure this out. You just punch it in your calculator. At any point, this is how fast the pumpkin was when it hit the ground at 6 meters. Now, in order to tell the change in velocity, what we have to do is we have to use our different distances, shorter ones, so we can see what build up to the point of where it hit the ground at 10.8 meters per second. So, as you can see below, what I've done is I've done the exact same formula. The only difference is I used 1 meter, 2 meters, 3, 4, and 5. This just shows you the velocity at which the pumpkin was at the first meter, second, third, fourth, and fifth. So you can put this on a graph, as shown here, to explain and see how the velocity actually changes in time. Now, theoretically, in an acceleration, where you have your velocity time graph will be actually a diagonal. However, in the real life, this doesn't always work. It doesn't work because you have factors that theoretically you can't put in, such as wind. Wind can take your object and push it different directions, so it affects the velocity of which it falls. It could make it go faster, slower, or it could even make it go off in direction. So that's why our graph isn't directly a diagonal line, even though it is roughly a diagonal. Now, last but not least, we can actually show the acceleration on a graph. However, with gravity, your acceleration is going to stay the exact same. It will always be negative 9.81 meters per second squared. That's just the rate that gravity falls. As you can see here, over the course of time, our gravity is just the exact same. It only goes through each of our time, which is 0.79 seconds, as we've timed. It just shows you that the acceleration stays directly the same over it. It just changes velocities. Now, if you hold up, we have a summary coming up that summarizes both uniform and accelerated motion for you. Stay tuned. This is our summary on our assignment. Uniform motion is an object that travels at equal distance in equal intervals of time. It does not matter how large or how small the time intervals may be. If we were to draw a distance time graph, or a DT graph, for uniform motion, it would be a straight diagonal line. In our experiment, we used a remote control car to represent uniform motion, where the car has a continuous speed that does not speed up or slow down. We decided it would be perfect for our experiment, as the speed can easily be controlled. For our experiment, we used our cemented driveway because it has a flat surface with no bumps or hills that could affect our data. We used some chalk to mark the distance the remote control car will be covering. Then we stood on different leveled ladders while we were filming so we can get different angles of the car crossing the lines for our videos. Why we did this to get the different angles would be because we want to make sure we could find the best possible angle to get our information from. In our distance time graph, the time and the distance both start at 0. And since the time and the distance is moving at a continuous speed, which stays unchanged throughout the experiment, this makes this graph have a line that is a diagonal. In our experiment, the car is moving with uniform motion, so our velocity doesn't change. So for our velocity time graph, it would be a straight horizontal line at a positive 2.7 meters per second. In our next experiment, we dropped a pumpkin off our balcony from approximately 6 meters off the ground to show acceleration. Acceleration is defined as the rate at which an object changes its velocity and would be classified as a vector quantity. A vector quantity would be something that has both magnitude and direction. This is normally symbolized by an arrow whose direction is the same as the quantity and whose length is proportional to the quantity's magnitude. For an object to be accelerating, it must be changing its velocity, which can mean that it is changing its magnitude or direction. Our velocity time graph for acceleration of our pumpkin falling, we have a bit of a curve on our graph instead of a straight diagonal line. Theoretically, our line should be a perfect diagonal, but ours isn't because we had different factors like wind, which would not show in our theoretical graph.
Let's see what you've got. Grab a piece of paper and pencil and we'll be asking you a few questions to see if you too can figure out the answers. Starting off, we'll have Brooklyn, aka Twinkle Toes, to ask you the few starting questions. Come on, Brooklyn, let's see what you've got.
Alrighty, starting off with an easy question. How many formulas are there for uniform motion? Now, I will give you 10 seconds so you can answer the questions. Alrighty, and the answer is 1. Question number 2. What is the formula for uniform motion? And the answer is V is equal to D over T. How many formulas are there for accelerated motion? And the answer is 5. The last question in this section. What kind of motion only deals with scalars? And the answer is uniform motion.
All right, let's keep the questions going. Up now, we have Olivia, otherwise known as the Klutz, up to ask you a few more questions. Come on, what do you got?
Okay, the question we're starting off with today is the velocity a vector or a scalar? I'll give you 10 seconds to think about it. Alright, the answer is a vector. Will velocity change with acceleration? If you got yes, you were correct. Do scalars have magnitude, units, and direction? Nope. They do not, so no is the answer. Time is measured in what? It is measured in seconds.
Next up here, we have Baylie, aka the Daredevil.
Alrighty, now for these last 4 questions, they're going to be a bit more difficult than the others, so you might want to write down this information. What is a vehicle's displacement if it travels at a velocity of 30.0 meters per second west for 15 minutes? We'll give you a few seconds to solve that. If you need more time, feel free to pause the video. Alrighty, have you come up with an answer? Well, the answer we got is 450 meters. If you got that, then feel free to congratulate yourself because you did a great job. Now for our second question. A car starts from rest and accelerates uniformly over a time of 5.21 seconds. For a distance of 110 meters, determine the acceleration of the car. We'll give you a few seconds to figure that one out. Well, let's see what the answer is. Alright, if you got acceleration equals 8.10 meters per second squared, you are correct. Alright, now let's move on to the third question. An airplane accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. We'll give you a few seconds to figure that out. Well, if you guessed 1,720, you were correct. Now for our last question. If you have a velocity of 2.5 meters per second and a time of 2.1 seconds, what is your displacement? Now we'll give you a few seconds to figure that one out. Now, if you got 5.25 meters, you were correct. Now, I'd like you to pat yourself on your back if you got any of these right.